If something moves or uses energy, it's a good bet that a mechanical engineer was probably involved at some point in its design. Now, we typically think of mechanical engineering on the moving parts, the machinery, the design of those types of things. And indeed, that is an important component of mechanical engineering. So the mechanical behavior of material or machine. So it's studying statics and dynamics, the strength of materials, what vibrations are generated by the operation of some machine, what is the reliability, the fatigue of the materials that are involved through repetitive use. There's of course the design of the machine elements, so the basic mechanical parts of gears and bearings and fasteners and everything else is going to be designed by a mechanical engineer. And then there's the manufacturing process, so the monitoring of engineering statistics, quality control for what's being produced in a factory, life cycle analysis. These are all things that are part of the domain of mechanical engineers as well. What doesn't always come to mind when we think about mechanical engineers is what we refer to as thermal design. So things like heat transfer, applications involving heat exchangers, air conditioning units, forced heating systems, the cooling of electronics, all of that is going to be governed by mechanical engineers' work. Fluid mechanics, so the study of fluid flow through pipes and air ducts, so fluids, not just talking about liquids, but gases as well. And then the study of thermodynamics, which starts to overlap into chemistry. So all of this falls under the domain of mechanical engineers, and we'll be taking a look at all of these elements as we go through our unit. Our first area of focus is going to be on heat transfer. Now, the vocabulary that we use for heat transfer stems from the fact that we originally conceptualized heat flowing like moving like a fluid, behaving like a fluid. So that's why we say it flows from one area to another, and some of the other vocabulary we use is reminiscent of a liquid or a gas and how it moves, even though that's not really the case. Now, there are three types of heat transfer that we'll take a look at. The first is thermal conduction. So this is where the energy passes through a solid, moving from the hot side to the cold side of the object. So if we think about a heated pot that warms the water on the inside, so you have the flame on one side or the heating element on one side of the pot, the water inside the other, so the heat flows through the walls of the pot and then warms the water. Then we have thermal convection. So this is where a fluid, like a liquid or a gas, moves between regions of different temperature. And so this could either be a natural occurrence, like hot air rising, or it could be forced, like with a fan, or a pump, like in an air conditioning type system. So that's thermal convection. And then finally, we have thermal radiation. So this is where energy is transmitted by electromagnetic radiation. So of course, like the sun is the obvious example that heats the earth, and then that energy, for example, could be used in a solar panel or for photosynthesis or whatever. So each of these different types of heat transfer has its own equation that governs its behavior. And so in the case of thermal conduction, we have Fourier's law of conduction. And so we've got some new types of variables that are presented to us that we need to make sure that we're familiar with. So the heat transfer variable Q with the dot above it is indicating that it is a rate. So it is a heat transfer rate for conduction through a plane, through a flat surface. And so the units on that are going to be watts if we're in SI units, or BTUs per hour. So obviously BTUs per hour, new unit for us, but we can see that as being a rate of energy per unit of time. And of course, remember, watts are joules per second. So we have energy transfer per unit of time. Then on the other side of the equation, we've got this K sub T, which is the thermal conductivity of the material. And so the units are listed here. This is just a constant that's unique to whatever material the energy is, the heat is being conducted through. So this could be different for a glass window pane versus a steel pot on the stove or a wall. So that's going to be something that's going to be measured in a laboratory. We've got the cross-sectional area. So this is basically the face of the wall or window or whatever it is through which we're conducting energy. We've got the temperature difference from the hot side to the cold side, and so it's always going to be the energy is always flowing from the hot side to the cold side. So it's always going to be subtracted in that order. And then finally, we've got this delta X in our equation, which is the thickness of the wall or the plate or the glass pane or whatever it is. So in the diagram we see in front of us, we can consider this to be the outside on a hot day, for example. This would be the inside of a car or a room or something like that. And then we have the window that separates those two, the glass plane in between. And so we've got the hotter temperature on this side, we've got the colder temperature on the inside, and then we're going to have the heat transfer that's going to be going from the hot side through the window pane to the cold side. And so this delta X, this is the width here of the window pane, and then the area is going to be the surface area between the outside and the inside. So in the situation we have here, we have a window that is a 2 foot by 3 foot pane. So that's going to give us the area. And then it has a thickness of 1/8 of an inch. So that's going to be our delta X in our equation. So we're told that the outside surface is this 21 degrees, the inside surface is 33 degrees. So we want to know what's the rate of heat loss through this window given this thermal conductivity constant. So we have the equation in front of us, so we're looking for that heat transfer rate. Again, in the case of conduction, it always flows from the hot side to the cold side, so it's always going to end up being a positive value since our temperature difference is always going to turn out to be positive. So we can plug in this 0.45 BTUs per hour per foot, and then this R variable here is the absolute measurement of temperature in the English units. So just like we have Celsius and Kelvin, where we can add 273 to end up on that absolute scale to transfer from Celsius to Kelvin, in English units, it's the Rankine scale, and so we add 460 to any temperature measurement in Fahrenheit to transfer it to an absolute scale. Now in conduction problems and in convection problems, as we'll see in a minute, we don't actually have to make the conversion to that absolute scale. And the reason is both those equations take the difference between the two temperatures, the hot side and the cold side, or as we'll see slightly differently, the ambient temperature and then the surface temperature in convection. And so since you're taking a temperature difference, whether you're in an absolute scale or on these relative scales in Fahrenheit and Celsius, the difference is going to be the same. So we don't actually have to make this adjustment. We'll see that we do have to make the adjustment to these absolute scales because of the nature of the radiation equation. But for now, we can just go ahead and ignore it. So we've got our thermal conductivity constant. We're going to have the area 2 feet by 3 feet, and then we're going to multiply that by the difference between the temperatures. So we've got 33 minus 21 degrees, and then that's over the delta X, so the thickness of the window, which is 0.125 inches. Now one thing we do have to be careful of, as always, is our units. Everything is in good shape. Yes, we have Fahrenheit and Rankine, but for the reason that I explained, we don't have to worry about it. We're in good shape here with the feet and feet here. We've got the BTUs, we've got hours. The one issue we have is on the inches here. We're going to have to make that conversion to feet by multiplying in the denominator here by 1 foot over 12 inches. Otherwise, the units are not going to work. So just keeping track of the units at this point, we're now looking at BTUs per hour, feet, and then again, this Rankine is the equivalent of Fahrenheit, so we're going to have a match there, as we'll see. For the area here, we're ending up with square feet. Over here in the last part of the equation, we've got Fahrenheit in the top, and then after we make the conversion here, we're going to have feet on the bottom. So checking to see what our units are going to work out to be, these 2 feet are going to cancel out with the feet squared on the top. The 2 temperature measurements are going to cancel out as well. And so the only thing that we have left is BTUs per hour, which indeed is what we want if we're looking for a heat transfer rate. So now, if we perform the arithmetic, we can get a heat transfer rate of 3,120 BTUs per hour. pretending like we had three significant figures everywhere.